Just as it would be impossible to fly a large modern aircraft safely without the flight instruments, it would also be impossible to fly it safely without the engine and aircraft systems instruments. The engine instruments are divided basically into two categories that are called either the performance indicators or the engine condition indicators. Performance indicators are thrust indicating instruments, such as the engine pressure ratio (EPR) gauge or the fan speed (N1) gauge. Engine condition indicators include the exhaust gas temperature (EGT) gauge, compressor speed, oil pressure and oil temperature gauges. We'll be discussing these and others later in the lesson. This diagram shows some of the parameters that we've just mentioned, and the position of the sensors that are required to measure them. There are two types of cockpit display: the analog display, a clockwork cockpit, or the electronic display, a glass cockpit. We'll be showing some of the instruments required in the clockwork cockpit as we go through the lesson. The glass cockpit displays will be described in detail in the latter part of the lesson. In the clockwork cockpit, there is a multitude of gauges displaying information. The glass cockpit is displayed on cathode ray tubes, CRTs, or liquid crystal display panels, LCDs, with light-emitting diodes, LEDs, for digital displays. Alongside the glass cockpit display, a small number of conventional gauges are retained in case of failure of the electronic displays. Both types of display convey essentially the same information to the pilot, but the flexibility of the glass cockpit system means that it's now taking over as the preferred means of showing both flight and engine instrumentation. Thrust measuring instruments are of two basic types. The type that measures the jet pipe pressure, the P7 gauge. The type that measures the ratio of two parameters, the jet pipe pressure and the engine air intake pressure, the EPR gauge. Turbopropeller aircraft measure and indicate engine torque, which is used to give an indication of engine power. Older low-ratio bypass engines, like the Rolls-Royce Conway, use the jet pipe pressure, P7, as an indication of engine power. The P7 system gauge can be marked in inches of mercury, pounds per square inch, or a percentage of the engine's maximum thrust. High-ratio bypass engines use the engine pressure ratio, EPR, as an indication of engine power output. The ratio is that between the exhaust pressure and the engine intake pressure. On some large turbofan engines, the values of the turbine discharge pressure and the fan outlet pressure are integrated. The figure thus obtained is then compared to the compressor inlet pressure to produce what is called integrated EPR. Pitot tubes, suitably positioned, sense the pressures which are required to work the system. The tubes can either be connected directly to the indicator in the cockpit or to a pressure transmitter which is electrically connected to the indicator. Turboprops and turboshaft engines develop their power by producing a preponderance of torque to turn the propeller, rather than pure thrust from their jet efflux. Torque, by definition, is a force applied at a distance to a turning point. The torque meter system measures, and its indicator displays, the power being produced by the engine. There are two main methods employed in measuring the torque of the engine. One uses oil pressure, and the second is an electronic device. The units of measurement vary between systems. The indicator gauges may be calibrated to read pounds per square inch or foot-pounds, Newton meters, brake or shaft horsepower. Engine torque is proportional to the horsepower being produced by the engine, and this is transmitted through the propeller reduction gear. The helical gear torque meter system depends on the axial thrust which is developed when helically cut gears are used to transmit power through the propeller reduction gear. The shafts of the gears rotate within cylinders, and the axial thrust they develop is balanced by oil pressure trapped inside the cylinders. Torque meter oil pressure is transmitted to a gauge in the cockpit. The gauge is calibrated in pounds per square inch. The system oil pressure, which in some systems can have quite a high value, for instance the Proteus engine is capable of developing about 800 pounds of torque, is generated by a torque meter system oil pump. In this system, which is similar to that used on the Rolls-Royce Dart engine, there is an oil pressure bleed hole within each cylinder. When the thrust developed by the helically cut gear is exactly balanced by torque meter oil pressure, the shaft of each helical gear takes up a sensitive position, partially covering the bleed hole. If engine power output increases, the axial thrust being transmitted by each gear increases, which forces its shaft further into its retaining cylinder. Thus the shaft is forced into a new position where it blocks the bleed hole. The torque meter oil pressure, being unable to escape, now builds up to a new, higher value, until it's able to force the gear shaft back into the sensitive position, where once again it's able to balance the axial thrust being developed by the helical gear. If the engine power output decreases, the axial thrust being transmitted by each gear also decreases, which allows its shaft to be displaced slightly out of the retaining cylinder. Thus the shaft is forced into a new position where it uncovers the bleed hole. The torque meter oil pressure now falls to a new lower value, until the lower axial thrust being developed by the engine is able to overcome it and force the gear shaft back into the sensitive position in the cylinder. Once this has happened, axial thrust is again balanced by oil pressure in the cylinder, but now it's balanced by a lower torque meter value. In addition to giving an indication of engine power output, the torque meter system can also be utilized to send signals to the auto feather and the water methanol injection systems. The auto feather system, as its name implies, will automatically feather the propeller of a failed engine. This is particularly important if the failure occurs on takeoff. The electronic system comprises two concentric shafts. The first shaft, which is called the torque shaft, connects the engine to the propeller reduction gearbox. The second shaft, the reference shaft, is connected only to the engine. An exciter wheel is fitted to the forward end of each shaft. The exciter wheels rotate past an electromagnetic pickup and produce an AC voltage. While the engine is stationary, the exciter wheels are aligned, but as power is increased, the torque shaft twists. This changes the phase relationship of the voltages produced. The change in phase relationship, which is used to drive an indicator through an amplifier, is proportional to the change in power. The RPM indicator is called a tachometer, tacho for short. There are three methods of measuring engine rotational speeds: the mechanical magnetic tachometer, the electrical generator system, the tacho generator, the inductive probe system. The measurement of engine speed is of vital importance if accurate control and monitoring of the engine can be achieved. The crankshaft speed of piston engines is measured. The RPM indicator is called a tachometer, a tacho. The usual method of measuring engine rotational speed on piston engines is the mechanical or magnetic tachometer. The mechanical tachometer consists of a flexible drive shaft and the tacho indicator. One end of the flexible drive shaft is connected to the tacho indicator in the cockpit. The other end goes to the accessory drive casing on the engine, where it's driven through gears from the crankshaft. The input drive causes a magnet in the indicator to rotate. The magnet rotates inside a copper or aluminium drag cup. This induces eddy currents in the aluminium drag cup. Eddy currents are caused by the magnetic field of the moving magnet acting on the electrons of any metal in the vicinity of the magnet. The eddy currents themselves generate a magnetic field which interacts with the magnetic field of the magnet. This interaction causes a torque or turning moment, which is established to turn the drag cup in the same direction as the permanent magnet. A shaft extends from the drag cup and is connected to a pointer. The turning motion of the pointer is against the tension of a hairspring, which controls the drag cup position and hence the position of the pointer. The flexible drive is driven at reduced speed, but true speed will be shown on the indicator. The indicator incorporates compensation devices for changes in temperature. The electrical generator system, sometimes called the tachogenerator system, is possibly the oldest form of engine speed measurement still in use on large aircraft. It utilizes a small three-phase generator, driven by the appropriate spool shaft. The output of this generator powers an indicator in the cockpit. The indicator is a synchronous squirrel cage motor that turns a drag cup assembly. The drag cup moves a pointer over a scale in a similar manner to that which we've just seen used in the mechanical system. In older aircraft, the indicator showed the actual revolutions per minute of the engine, but it's much more common to have the speed displayed as a percentage of the maximum engine speed. The speed of rotation of each of the spools is displayed. N is the SI symbol for rotational speed. Thus, in a triple spool engine, the speed of the low-pressure compressor, the fan, would be displayed as N1. The intermediate spool speed would be shown as N2, and the high-pressure compressor rotational speed would be N3. It's probable that there would always be provision on the high-pressure compressor spool for driving a tachogenerator through the external gearbox, which is driven by the high-pressure compressor shaft. But it may not always be possible to have gearboxes driven by the other compressor shafts. In this case, a speed probe could be used. There are two ways that the speed probe can generate the pulses required to feed the system. The first method uses the fan blades to excite the magnetic field of the sensor head of the speed probe as they pass it. The excitations generate a waveform which has a frequency proportional to the rotational speed of the fan. The second system uses a phonic wheel, which is part of the compressor shaft. The teeth of the phonic wheel pass through the magnetic field of the sensor, and thus generate pulses at a frequency which is proportional to the rotational speed of the shaft. The output of the sensor is amplified before being sent to the gauge. The advantage of the speed probe system is twofold. First, the reduction in the number of moving parts required in the engine, and second, that a number of separate electrical outputs additional to those required for speed indications can be provided. For example, automatic power control and flight data acquisition systems. RPM indicators, which receive their speed signals directly from speed sensors or via servo-operated systems, are powered from the aircraft supply. In the event of either a power supply failure or a signal failure, the needle of the indicator is returned to an off-scale position, and a power-off flag may be displayed. Clockwork cockpit instruments have displays which show percentage rotational speed, with 100% corresponding to the maximum spool RPM. Two scales are used: a main scale calibrated 0 to 100% in 10% increments, and a second pointer displays rotational speed in 1% increments. In line with other instruments, coloured arcs or indicator lines are used to show ranges and limits of engine speed. A green arc will represent the normal operating range, and an amber arc will denote a caution range. Red arcs show either the maximum speed of the engine or RPM ranges which are restricted, perhaps because vibration may be encountered within them. The glass cockpit uses a mixture of analog and digital displays on the same dial. This type of analog display is very useful in two ways. Firstly, for instantaneous comparison of multi-engine states, and secondly, the digital readout is a very accurate indication of individual engine states when they're required. If a parameter limitation is exceeded in the glass cockpit type of display, the whole of the dial displaying that particular parameter will change to either amber or red, depending on how far the limitation has been exceeded. On some older glass cockpit instrumentation, vertical ribbon displays are used. Many multi-engine aircraft are provided with a visual indicator, which is called a synchroscope, which indicates the RPM difference between the slave engines and the master. As you can see from this picture, the presentation consists of miniature propellers which rotate to show when an RPM difference exists, and whether the slave is faster or slower than the master. Gas turbine engines are heat engines. The power gas turbine engines produce is directly proportional to the heat released during the combustion of the fuel. Engine components and systems are designed to withstand certain temperatures. If their temperature limits are exceeded, they will fail. To allow safe operation, the engine temperatures must be monitored. The following temperatures are monitored on gas turbine engines: engine air inlet temperature, exhaust gas temperature, engine oil temperature, and internal air systems temperature. The temperatures monitored may range from -56 degrees Celsius to +1200 degrees Celsius. Different sensors are used depending on the temperature range to be monitored. There are four major types of temperature measuring device. They are the expansion type, which relies on the principle that most solids, liquids, and gases expand and contract with temperature changes. Two examples of the expansion type of device are the mercury thermometer and the bimetallic strip. The vapor pressure type of device uses the principle that liquids, when subjected to a rise in temperature, change their state from liquid to vapor. By measuring the pressure of the vapor, an indication of temperature can be gained. A change in the temperature of some electrical conductors, for instance platinum, will cause a change in the electrical resistance of that conductor. Measuring the change in the resistance of this conductor will indicate its temperature. This type of sensor is called the resistance type or the temperature bulb. In 1822, Thomas Seebeck accidentally discovered that heating the junction of two dissimilar metals will produce an electrical potential that is a function of temperature. If the junction is contained within a closed loop, the value of the potential will be dependent on the difference in the temperature between the junction where the heat is applied, the hot junction, and the other end of the loop, the cold junction. Examples of the use of thermocouples include the measurement of cylinder head temperature and turbine gas temperature. A radiation pyrometer is a device which can convert radiated energy into electrical energy. It consists of a photovoltaic cell and a lens which focuses the radiated energy onto the cell. The pyrometer is positioned so that the lens can be focused directly onto the heat source, in this case the turbine blades. The photovoltaic cell converts the radiated energy emitted by the blades into electrical energy, which is passed through an amplifier to an instrument calibrated in degrees Celsius. The temperature of the gas passing through the turbine of a gas turbine engine is the most critical parameter of those displayed on the engine instruments. Operation of the engine beyond the limits of turbine temperature, even for only a moment, is liable to cause excessive turbine blade creep, which will be catastrophic if the rotating blades touch the casing of the engine. The gas temperature must be monitored closely, and automatic temperature limiting equipment is fitted to most gas turbine engines operating today. To enable this monitoring to be achieved, temperature probes are inserted in the gas stream. Temperature probes are formed from the junction of two dissimilar metals, which, as we've just seen, generate a potential when the junction is heated. The potential is proportional to the temperature applied to the junction. This diagram shows how the terminals for the connections to the probes, which are the hot junctions, are connected, and also how the gas flows over them. The output from the probes is sent to the cockpit engine instrument, which is the cold junction. Here the potential is displayed on a very sensitive millivoltmeter calibrated to show the engine gas temperature. A single probe would not supply enough information to accurately tell the pilot what was going on in the whole of the turbine. It could only inform him about a small part of the turbine that it was monitoring. Additionally, a failure of that single probe would rob the pilot of his knowledge of the most important of the engine parameters. To gain complete awareness of the temperature situation, it's necessary to place a number of probes around the periphery of the turbine or the exhaust system. The probes are connected electrically in parallel. Their output is thus the average of all of the probes. Connecting the probes in parallel has the added advantage that if one probe is damaged, their electrical output, and therefore the temperature reading on the gauge, is virtually unaffected. The position of the probes in the engine depends upon two things: the anticipated maximum temperature of the gas and the ability of the probe material to withstand that temperature. The industry standard for the material used at the junction in the temperature probes in gas turbine engines is chromel, nickel chromium, and alumel, nickel aluminium. These two materials may not have the highest millivoltage output of the materials available, but their ability to withstand very high temperatures, coupled with a reasonable volts per degree ratio, makes them ideal for the job. The system does not require a power supply for the gauges to work. However, if the potential generated by the probes is to be used to supply a temperature limiting system, the output will need to be amplified. The power required for amplification will be supplied by the aircraft's electrical system. If it's required that the probes supply both a temperature limiting system, otherwise known as a top temperature control, and a temperature indicating system, they will contain two separate junctions, one to feed the temperature limiting system and one to feed the indicator. On the type of engine where the temperature of the gas within the turbine is too high for the metal of the probes to stand it, the probes may be positioned after the turbine and the gauge calibrated to read exhaust gas temperature, or EGT. On other engines, it may be found convenient to combine the temperature probes with the pitot probes, which measure exhaust gas pressure, P7. In this case, the gauges will read jet pipe temperature, or JPT. Obviously, it would be ideal if the temperature could be sampled either before the turbine, when it would be called either turbine inlet temperature, or TIT, or turbine entry temperature, TET. Alternatively, the gas temperature could be sampled inside the turbine, when it would be called turbine gas temperature, or TGT. In every case, the position of the probes is dependent upon their ability to withstand the temperatures they encounter. Actual blade temperature can be measured by the radiation method, with the use of an optical pyrometer. Air temperature is one of the basic parameters used to establish data vital to the performance monitoring of aircraft engines, for example, thrust settings, fuel-air ratio settings, etc. The ideal temperature to suit these requirements is that sensed under static conditions at various flight levels. This temperature is called variously the outside air temperature or static air temperature, SAT. Unfortunately, this measurement can be affected by the adiabatic compression that occurs with increase of aircraft speed. Below 0.2 Mach, the temperature of the air sampled is very close to SAT. but at higher Mach numbers, an increase in skin friction will raise the air temperature. This increase in air temperature is commonly referred to as ram rise, and the temperature that's indicated is called ram air temperature, RAT, which is the static air temperature plus the increase caused by the ram rise. The ram rise can be computed by air data computers to correct the indicators to SAT, or alternatively calculated mathematically for each type of aircraft as a function of Mach number, and tables or graphs can be included in their flight manuals. For use in the instruments of aircraft which fly at high Mach numbers, total air temperature, TAT, is measured. The air is brought to rest, or nearly so, without the addition or removal of heat. Total air temperature equals static air temperature plus ram air temperature plus friction rise. Temperature indicators use coloured arcs to show their operating range. Green for normal, amber for caution, and red upper or lower limits. Pressure is defined as force per unit area. Pressure is normally indicated either as pounds per square inch or inches of mercury. When we're discussing pressure measurement, we must use the following terms: absolute pressure and gauge pressure. Absolute pressure is measured relative to absolute zero pressure, the pressure that would occur at absolute vacuum. Thus, the absolute pressure on the Earth's surface at sea level is the atmospheric pressure, which is 14.7 pounds per square inch. The more usual pressure measured by most gauges is called gauge pressure. Gauge pressure reflects an adjusted pressure that reads zero at the Earth's surface. Elastic pressure sensing elements are used to measure pressure. Forces are produced within the elements by applied pressures, and these forces are converted to mechanical movement. The mechanical movement is then used to operate either a direct reading gauge or an electrical transmitter. The sensing elements commonly used are diaphragms, capsules, bellows, and Bourdon tubes. A diaphragm is a sheet of a semi-flexible material, anchored at its periphery, and most often round in shape. It usually serves as a barrier between two chambers, moving slightly into one chamber or the other, depending on differences in pressure. Diaphragms are used to measure low pressures. Capsules are made up of two diaphragms placed together and joined at their edges to form a chamber. The chamber may be sealed, in which case the device is called an aneroid capsule, or it may be joined to a pressure source, in which case it's called a pressure capsule. Like diaphragms, capsules are also used to measure low pressure, but capsules are more sensitive to small pressure changes. The bellows element can be considered as an extension of the corrugated diaphragm principle. It may be used for high, low, or differential pressure measurement. Typically, the bellows element is used to measure pressures like the output of an aircraft low-pressure fuel booster pump. The Bourdon tube is the oldest of the devices used for sensing pressure. The element is essentially a length of metal tube with an elliptical cross-section and shaped into a letter C. One end of the tube is sealed and called the free end. The other end is connected to the pressure source and fixed. When pressure is applied, the tube tries to straighten. This movement is magnified to drive an indicator pointer. The Bourdon tube can be manufactured to indicate high or low pressures, but it's normally associated with higher pressures such as engine oil pressure. As well as the actual pressures, warnings can be displayed to the pilot by pressure-operated switches. These switches can operate for low, high, or incorrect differential pressure. A differential switch or gauge is subjected to pressure on both sides of its sensor. In many of the systems associated with the operation of the aircraft and its engines, liquids and gases are used, the pressures of which must be measured and indicated. The gauges and indicating systems fall into two categories: direct reading and remote indicating. A remote indicating system uses a remotely positioned sensing element which is connected to the pressure source. The sensing element translates the actual pressure reading into an electrical signal. The sensing element then sends the signal via electrical wiring from its remote position to an instrument in the cockpit. A direct reading pressure instrument is physically connected to the source of the pressure that it's sensing. For instance, a direct reading engine oil pressure gauge will be connected via an oil pressure pipeline directly to the engine, to the point where the oil pressure is to be measured. Coloured arcs of green, amber or red are used to indicate the range and limits of the pressure system. Vibration monitoring equipment is fitted to almost all commercial jet engine aircraft. Although gas turbine engines have an extremely low vibration level, any change in that level is usually indicative of damage which may lead to failure. Warnings will be given in the cockpit if the vibration levels are exceeded, and some systems have a continuous readout of vibration levels. Modern engines have the facility whereby the vibration level of each rotating assembly can be monitored, so that the source of any vibration can be pinpointed. The principle upon which vibration monitoring equipment works requires an input from a detector, which can be either a piezoelectrical crystal mounted strategically on the engine, or a fixed coil carrying 115 volts at 400 Hz, the output of which will be affected by the movement of a magnet within it, which is mounted on springs. In either case, the frequency of the incoming vibrations will be amplified, and then filtered so that only those frequencies that are indicative of damage occurring to the engine will affect the output. The output of the detector will affect the current flowing through the coil into the amplifier and filter. The filter will erase any output which is normal to the engine, but allow through to the amplifier any frequency that's considered to be harmful to the engine. The result of this amplification is sent to the instrument via the rectifier and warning circuit. The needle will show the appropriate deflection for the amount of vibration being suffered by the engine at that time. If the level of vibration exceeds a predetermined amount, a warning light on the instrument illuminates. Vibration is measured and displayed in relative amplitude. There are two methods of indicating the quantity of fuel carried in an aircraft. Either the volume, for example gallons, or the mass, kilograms or pounds, are measured. Because the mass of the fuel on board is of more interest to the pilot of a large aircraft than is the volume of the fuel on board, measurement of the volume of fuel is now only used on light aircraft. The simplest form of volume indication is a float system. Early aircraft used a float which sat on the surface of the fuel in the tank. Attached to the float was a piece of wire that protruded out of the top of the fuel tank. As the fuel level reduced, so the wire disappeared from view. A later system used the float to reposition a wiper on a variable resistor. This varied the current flowing to an indicator which had a pointer that moved over a scale calibrated in volume. The system was powered by direct current. The disadvantage of the float system is that the indication is not linear, and there is no provision for making adjustments for system accuracy. The gauge is set to be accurate at the low and empty positions. The system is also subject to errors caused by temperature changes, aircraft attitude changes, and aircraft acceleration. In its basic form, a capacitance system, which is much more accurate than the float system, consists of a tank unit, which is effectively a variable capacitor, located in the fuel tank, together with an amplifier and an indicator. A tank unit consists of two concentric aluminium alloyed tubes which are held apart by pairs of insulating pins. The coaxial electrical connections are insulated and the unit is insulated from the tank. The principle of operation of the capacitance system is based on the use of fuel and air as the dielectric between parallel plate capacitors, which have a fixed area and a fixed distance between them. The only variable in the system is then the ratio of the dielectrics used, which are fuel and air. That ratio is determined by the quantity of fuel in the tank. Incorporated in the system are reference units, which reduce indication errors that would occur if the dielectric constant of the fuel changes from its normal value, which is about twice that of air, and directly proportional to its density. Reference units are located on the lower end of a tank unit, and are always totally submerged in the unusable fuel that remains in the tank. The circuit is compensated for changes in temperature, and will indicate the mass of the fuel in the tanks. Fuel gauging systems can incorporate an additional indicator known as the fuel totalizer, which can indicate the sum of all of the tank quantities. In the event of a gauge failure, the fuel gauging system will fail safe and drive the needle of the failed indicator slowly to the 0 position. A test circuit is incorporated, which will simulate gauge failure. Place your cursor over the test button to activate the test. When the test switch is released, the pointer should return to its original position. If water is present in the fuel, it can cause errors in the indicating system. If the percentage of water is very large, the capacitors in the sensing units can be effectively shorted out. If this happens, the indicator needle will be driven beyond full scale. As well as the quantity of fuel measured, the instantaneous fuel flow can be shown. To obtain the indication of total fuel used, the instantaneous fuel flow must be integrated. The fuel flow meter can display either volume flow or mass flow. To indicate mass flow, the meter must be compensated for the density of the fuel. A fuel pressure gauge can be adapted to be used as a simple flow meter. This system is used on many light piston engine injection systems. Most gas turbine engines use an electrical sensor, which utilizes the change in either the torque output or the rotational speed of an impeller situated in the high-pressure fuel line to the fuel spray nozzles. This type of fuel flow meter consists of a cylindrical light alloy casting, within which are guide vanes that support the shaft of a helical vane impeller. The impeller has a magnet embedded in it. Electrical pick-off coils are situated in the wall of the cylinder casting. When the fuel flow rotates the impeller, a sinusoidal signal is induced in the pick-off coils. The frequency of the sinusoidal signal is proportional to the speed of the rotor, which in turn is proportional to the rate of flow. The total consumption is obtained by integrating the rate of fuel consumption over time. A flow meter that displays fuel consumed as well as fuel flow is called an integrated flow meter. Modern aircraft employ remote indicating systems that can be powered by either direct current or alternating current supplies. Whatever the power source, each data transmission system employs a remotely positioned transmitter located at the source of the information, and a receiver which responds to the information received. The DESIN transmission system is a simple transmission system with low torque characteristics, which is used for the remote indication of angular position. It's often used where a simple pointer and scale is adequate. For example, remote indication of flap, rudder and elevator positions, or to repeat the reading of an instrument at a remote point. The accuracy of the system is approximately ±2%. The transmitter consists of a continuous resistance ring or potentiometer which has three fixed tappings, A, B and C, spaced 120 degrees apart, which are connected to the receiver. The input shaft carries two diametrically opposed spring-loaded sliding contacts, or wipers, which are in contact with the potentiometer. The wipers are fed via slip rings and brushes with direct current. The receiver consists of three high-resistance coils, whose axes are spaced 120 degrees apart, with a permanent magnet rotor pivoted at their center carrying a pointer shaft. The three coils are connected to the tapping points A, B and C in the transmitter. When direct current is applied to the transmitter wipers, the voltages at the tapping points A, B and C produce a current flow in the three stators of the receiver, and a resultant magnetic field is produced. The rotor magnet aligns itself with this magnetic field. The magnitude and polarity of each tapping point voltage varies according to the position of the wipers, and thus, if the input shaft is rotated, the change of voltages at A, B and C produces a variation in the current flowing in the stator coils, and rotation of the resultant magnetic field in sympathy with the rotation of the input shaft. The rotor magnet remains aligned with this field at all times, and so rotates in synchronism with the input shaft. Here the voltage distribution around the potentiometer is such that point A is at plus 24 volts, while points B and C are both at plus 8 volts. Because the voltage at A differs from that at B and C by the same amount, current flows from A through coil A in the receiver, then divides equally at the star point, with half the total current flowing through coil B and half through coil C back to the transmitter. The resultant magnetic field in the receiver, with which the rotor magnet aligns itself, is compounded from the vectors representing the individual fields. If the input shaft is rotated through 120 degrees in a clockwise direction, as shown here, the voltage distribution around the potentiometer is such that the current flows from B through coil B in the receiver, then divides equally to flow through coils A and C back to the transmitter. The vectors show that the resultant magnetic field also rotates through 120 degrees clockwise, and the rotor shaft aligns itself along this new axis. Thus, if the wipers in the transmitter are placed in any position by the input shaft, the resultant field at the receiver, and hence the rotor magnet, takes up a corresponding position. If a pointer moving over a calibrated scale is attached to the rotor, remote indication of the position of the input shaft is immediately available. The DESIN system has inherent errors caused by the wiper arm being in physical contact with the potentiometer. This causes inaccuracies due to friction and carbon contamination of the resistor. The Celsin was developed in 1925. Halfway through the Second World War, the Americans reinvented the Celsin and caused it the Synchro. The Celsin is a system whereby a transmitter and a receiver, powered by alternating current, are electrically connected so that angular rotation of the rotor in the transmitter is reproduced simultaneously in the receiver. The transmitter consists of a stator and a rotor. The stator has three electrical coils whose axes are 120 degrees apart. The three stator coils are star-connected. The rotor is mounted on a shaft and has one electrical winding, the two ends of which terminate in two slip rings. Carbon brushes feed power to the rotor through the two slip rings. The receiver is identical to the transmitter, and they are connected electrically to each other as shown here. The two rotors are supplied by alternating current from the same source. With power applied, both of the rotors will adopt the same position relative to their stators. The rotor of the transmitter can be attached to the output shaft of any device which needs positional information communicating to a remote position. The magnetic flux generated in the coil of the rotor interacts with the cores of the stator and causes a current to flow in their windings. Because the stator coils of the transmitter and receiver are in series with each other, the stator coils of the receiver now have a magnetic field around them which is identical to that around the stator coils in the transmitter. The rotor in the receiver aligns itself with the magnetic field which is formed in the receiver stator, adopting a position which is identical to that of the transmitter stator. The synchro system is more accurate than the desin system. Some aircraft indicate and record usage of their engines in flight. The flight hour meter can be coupled to an airborne sensor which energizes it at certain airspeeds. The information obtained from the flight hour meter can be used to determine the time to run between engine servicing periods. The display of the parameters associated with engine performance and airframe systems control by means of cathode ray tube type display units has, like those of flight instrument systems, become a standard feature of many types of aircraft. The display units form part of two principal systems, called the Engine Indicating and Crew Alerting System, ICAS, and Electronic Centralized Aircraft Monitoring, ECAM system. These systems were first introduced in Boeing 757 and 767 aircraft and the Airbus A310 respectively. As far as ICAS is concerned, engine operating data is displayed on its cathode ray tube units, thereby eliminating the need for traditional engine instruments. Engine operating data, as well as that relevant to other systems, is not necessarily always on display. But in the event of malfunctions occurring at any time, the flight crew's attention is drawn to them by an automatic display of messages in appropriate colors. However, in the Airbus A310, in which system operation was displayed in checklist and schematic form, the early ECAM concept was based on the view that engine data needed to be displayed during the whole of a flight, and accordingly traditional engine instruments were retained. It's of interest to note, however, that in subsequent types produced by this manufacturer, for example the A320, the ECAM system is developed to include the display of engine data in one of its display units. The basic ICAS system comprises two display units, a control panel which is called the Display Select panel, and two computers which are supplied with analog and digital signals from engine and system sensors. The computers are designated left and right, and only one is in control at a time. The other is on standby, and in the event of failure, it may be switched in either automatically or manually. Operating in conjunction with the ICAS system are discrete caution and warning lights, which are situated on the front coaming, a standby engine indicator panel, and a remotely located panel for selecting maintenance data displays. The system provides the flight crew with constantly displayed information on primary engine parameters and with secondary engine parameters and advisory, caution, warning alert messages displayed as required. The display units provide a wide variety of information relevant to engine operation and operation of other automated systems, and they utilize color cathode ray tubes. The units are mounted one above the other. The upper unit displays the primary engine parameters, N1 speed, exhaust gas temperature, and warning and caution messages. In some cases, this unit can also display the engine pressure ratio, depending on the type of engines installed and on the methods used to process data by the thrust management control system. The lower unit displays secondary engine parameters, that is N2 speed, fuel flow, oil quantity, pressure and temperature, and engine vibration. In addition, the status of non-engine systems, for example, flight control surface positions, hydraulic systems, the auxiliary power unit, etc., can also be displayed, together with aircraft configuration and maintenance data. The row of V's shown on the upper display unit only appears when secondary information is being displayed on the lower unit. 7 colours are produced by the cathode ray tubes, and they are used as follows. White, all scales, normal operating range of pointers, digital readouts. Red, warning messages, maximum operating limit marks on scales, and digital readouts. Green, thrust mode readout and selected EPA and End1 speed marks or target cursors. Blue, system testing only. Yellow, caution and advisory messages, caution limit marks on scales, digital readouts. Magenta, during in-flight engine starting and for cross-bleed messages. Cyan, names of all parameters being measured, for example N1, oil pressure, TAT, etc., and status marks or cues. ICAS is designed to categorize displays and alerts according to function and usage, and for this purpose there are 3 modes of displaying information. 1. Operational, 2. Status, and 3. Maintenance. Operational and status modes are selected by the flight crew on the Display Select panel, while the maintenance mode is selected on the maintenance panel, which is for the use of ground engineering staff only. The operational mode displays the engine operating information and any alerts which are required to be actioned by the crew. Normally, only the upper display unit presents information. The lower one remains blank, but it can be selected to display secondary information as and when required by pressing the Engine button on the Display Select panel. Use your mouse to press the Engine button on the Display Select panel to see secondary information being shown on the bottom screen. When selected by pressing the Status button on the Display Select panel, the Status mode allows data to be displayed on the bottom screen, which is used to determine the dispatch readiness of an aircraft. This data is closely associated with details contained in the aircraft's minimum equipment list. The display on the bottom screen shows positions of the flight control surfaces in the form of pointers registered against vertical scales, selected subsystem parameters, and equipment status messages. Selection is normally done on the ground, either as part of the pre-flight checks of dispatch items, or prior to shutdown of electrical power to aid the flight crew in making entries in the aircraft's technical log. Use your mouse to press the Engine and Status buttons on the Display Select panel to change the information shown on the bottom display between engine secondary information and the status display. The Maintenance mode provides maintenance engineers with information in 5 different display formats to aid them in troubleshooting and verification testing of the major subsystems. This display shows an example of the ECS MSG maintenance page on the bottom screen. The top screen displays data in a compact format. This display shows an example of the electrical hydraulic maintenance page. The displays, which are presented on the lower display unit, are not available in flight. The Display Select panel permits control of ICAS functions and displays, and can be used both in flight and on the ground. It's located on the center pedestal on the aircraft flight deck. Moving your mouse cursor over each control will display the purpose of each of them. The system continuously monitors a large number of inputs, typically over 400 from engine and airframe system sensors, and will detect any malfunctioning of systems. If any malfunction should occur, then appropriate messages are generated and displayed on the upper display unit in a sequence corresponding to the level of urgency of action to be taken. Up to 11 messages can be displayed on the top line at the left of the display screen and at the following levels. Level A. Warning requiring immediate corrective action. Level A warnings are displayed in red. Master warning lights are also illuminated, and aural warnings, for example the fire bell, from a central warning system are given. Level B. Cautions requiring immediate crew awareness and possible action. These are displayed in amber and also by message caution lights. There is also an aural tone which is repeated twice. Level C. Advisories requiring crew awareness. Advisories are also displayed in amber. No caution lights or aural tones are associated with this level. In order to differentiate between a caution and an advisory, the latter is always indented one space to the right. When a new fault occurs, its associated message is inserted on the appropriate line of the display. The occurrence of a new fault may cause older messages to move down one line. For example, a new warning message would cause all existing warning, caution and advisory messages to move down one line. A message is automatically removed from the display when the associated condition no longer exists. In this case, messages which appear below the deleted one each move up a line. If there are more messages than can be displayed at one time, the whole list forms what is termed a page, and the lowest message is removed, and a page number appears in white on the lower right side of the list. If there is an additional page of messages, it can be displayed by pushing the Cancel switch on the ICAS Caution and Annunciator panel. We'll show the ICAS Caution and Annunciator panel shortly. Warning messages are carried over from the previous page. The captain and first officer each have a dual-purpose warning caution light on their side of the glare shield. Part of the ICAS Caution and Annunciator panel is used to position cancel switches and a recall switch. Pushing the cancel switch removes only the caution and advisory messages from the display. The warning messages cannot be cancelled. Moving your mouse cursor over each control or indicator will display their purpose. If the lower display unit should fail when secondary information is being displayed on it, an amber alert message appears at the top left of the upper display unit, and the information is transferred to it as shown here. The format of this display is referred to as compact, and it may be removed by pressing the Engine switch on the Display Select panel. Failure of a display unit causes the function of the status switch on the Display Select panel to be inhibited, so that the status page format cannot be displayed. If the Display Select panel fails, the advisory message ICAS Control panel appears at the top left of the upper display unit, together with the primary information, and the secondary information automatically appears on the lower display unit. The cancel recall switches do not operate in this failure condition. The standby engine indicator provides primary engine information in the event that a total loss of ICAS display occurs. information shown on the standby engine indicator relates to N1 and N2 speeds, EPA and EGT, and the displays are of the LCD type. Operating limit values are also displayed. Moving your mouse cursor over each part of the indicator will display the purpose of it. The Maintenance Control Panel is for use by maintenance engineers for the purpose of displaying maintenance data which is stored in system computer memory during flight or ground operations. Moving your mouse cursor over each control or indicator will display its purpose. The units that comprise the ECAM system, as it was originally developed for the Airbus A310, are shown in this functional diagram. As far as the processing and display of information are concerned, the ECAM system differs significantly from ICAS in that the displayed data relates essentially to the primary systems of the aircraft and is shown in checklist and pictorial or synoptic format. Engine operating data is displayed by conventional types of instruments. Other differences between the ICAS and the ECAM systems relate to display locations and methods of selection of system operating modes. The display units are mounted side by side in the early version of the A310. The left-hand unit is dedicated to information on the status of systems, warnings, and corrective action in a sequenced checklist format, while the right-hand unit is dedicated to associated information in pictorial or synoptic format. In this example, both the names and the symbols of unlocked doors are shown in amber. The symbols of locked doors are shown in green, while their names are in white font. There are 4 display modes, 3 of which are automatically selected. The first is referred to as flight phase related. The second is the advisory mode and status. The third mode is failure related. The fourth mode is selected manually and called the aircraft system display. In normal operation, the flight phase-related mode automatically displays graphics appropriate to the current phase of aircraft operation. Those phases could be pre-flight, takeoff, climb, cruise, descent, approach, or after landing. In this example of the pre-flight phase, the left-hand display unit displays an advisory memo mode, and the right-hand unit displays a diagram of the aircraft's fuselage, doors, and arming of the escape slides deployment system. Status messages, which are also displayed on the left-hand display unit, provide the flight crew with an operational summary of the aircraft's condition, possible downgrading of auto-land capability, and, as far as possible, indications of the aircraft status following all failures except those that do not affect the flight. This example of an advisory display shows any aircraft limitations caused by the condition of the aircraft in blue font. Any systems or system functions which have been lost or affected in yellow font, and any further information deemed to be useful in white. The failure-related mode takes precedence over the other 2 automatic modes and the manual mode. In this example of a failure-related mode display, while taxiing out for takeoff, the temperature of the brake unit on the rear right wheel of the left main landing gear bogie has become excessive. A diagram of the wheel brake system is immediately displayed on the right display unit, and simultaneously the left unit displays the corrective action to be taken by the flight crew. As the corrective action is carried out, the instructions on the left-hand display are replaced by a message in white confirming the result of the action. The diagram on the right-hand display unit is appropriately redrawn as its system parameters change. In this example, the failure-related mode warning relates to a single system, and by convention, such warnings are signified by underlying the system title displayed. In cases where a failure can affect other subsystems, the title of the subsystem is shown boxed, as is shown in this example. Warnings and the associated lights are cleared by means of clear push-button switches on the ECAM control panel. The aircraft system display mode permits the selection of diagrams related to any one of 11 of the aircraft systems for routine checking, and also the selection of status messages, provided no warnings have been triggered for display. The selections that determine which systems are displayed are made by means of illuminated push-button switches on the system control panel. The layout of the ECAM control panel is shown here. All of the switches, with the exception of those for display control, are of the push-button illuminated caption type. Moving your mouse cursor over each control or indicator will display its purpose. This concludes the Engine Instruments lesson.